In April, a team at the University of Cambridge published a paper in the astrophysical journal Letters announcing that the James Webb Space Telescope had detected dimethyl sulfide in the atmosphere of a planet 124 light-years from Earth. On Earth, dimethyl sulfide is produced exclusively by living organisms, primarily marine phytoplankton. No known geological or chemical process generates it without biology. The detection was at roughly 3 sigma significance, which in statistics means there is about a 1 in 700 chance that it is a false positive. That is not proof. It is not confirmation. The lead author, Niku Madhusudan, was careful to say it provides the strongest evidence to date of possible biological activity on an exoplanet. Other teams pushed back. A NASA-led study published in July 2025 found the evidence inconclusive, noting that the signal was sensitive to how an instrumental offset in the data was treated. A separate analysis spanning 661 molecules argued that other sulfur compounds could produce similar spectral features. The debate is ongoing. Nobody has proved life exists on K2-18b. Nobody has proved it does not. But here is what matters. For the first time in human history, the question of whether life exists beyond Earth is no longer philosophical. It is observational. We are measuring the atmospheres of specific planets around specific stars and arguing about specific molecules at specific statistical confidence levels. That is a fundamentally different kind of conversation from the one Enrico Fermi started in 1950 when he looked up from his lunch at Los Alamos and asked the question that has haunted physics ever since. If the universe is so old and so vast, where is everybody? Stay with me, because the answer to that question looks very different in 2026 than it did even 5 years ago. The Fermi Paradox is not a puzzle about whether aliens exist. It is a puzzle about scale. The observable universe contains roughly 200 billion galaxies. The Milky Way alone contains between 100 and 400 billion stars. Current estimates based on data from the Kepler mission and ground-based surveys suggest that roughly 1 in 5 sun-like stars has an Earth-sized planet in its habitable zone, the orbital distance where liquid water could exist on the surface. That means the Milky Way alone may contain somewhere between 10 and 40 billion potentially habitable planets. The universe is approximately 13.8 billion years old. The Earth is 4.5 billion years old. The Milky Way is roughly 100,000 light-years across. Even at a fraction of the speed of light, a civilization capable of interstellar travel could theoretically colonize the entire galaxy in somewhere between 1 and 10 million years. That sounds like a long time. It is not. It is less than 1/10% of the age of the galaxy. If even one civilization anywhere in the Milky Way had developed interstellar travel at any point in the last 10 billion years, the math says we should see evidence of them everywhere. We do not. That silence has roughly 4 categories of explanation, and recent research has sharpened each of them considerably. The first category says life itself is rare. This is the rare Earth hypothesis. The argument is that while rocky planets and habitable zones may be common, the specific chain of conditions required for complex life is extraordinarily unlikely. Earth is not just the right distance from the right kind of star. It has a large stabilizing moon created by a specific giant impact 4.5 billion years ago that keeps its axial tilt from wandering chaotically. It has a magnetic field generated by a liquid iron core that shields the surface from solar wind and cosmic radiation. It orbits in a relatively calm region of the galaxy, far from the dense radiation-rich core. It has plate tectonics which recycle carbon and regulate atmospheric temperature over geological timescales. It has Jupiter, a massive gas giant whose gravity sweeps up asteroids and comets that might otherwise bombard the inner solar system at rates too high for complex life to survive. Each of these conditions individually is not necessarily rare. All of them together on the same planet at the same time may be. A 2024 paper published in Nature Astronomy by Crawford and Schulze-McCouch argued that the transition from microbial to complex multicellular life may be the critical bottleneck, noting that on Earth, single-celled organisms existed for roughly 2 billion years before anything multicellular appeared. If that transition is genuinely difficult, the galaxy could be full of microbial life and almost entirely empty of anything that builds radio transmitters. If you are the kind of person who stays for the real science, drop a like right now because it genuinely helps this kind of content reach more people who want to hear it. The second category says civilizations exist but destroy themselves before they become detectable. This is the Great Filter. The idea, originally formulated by economist Robin Hanson in 1998, proposes that somewhere between dead chemistry and galaxy-spanning civilization, there's at least one step so difficult that almost nothing gets past it. The question is whether that filter is behind us or ahead of us. If it is behind us in the origin of life itself, or in the jump to multicellularity, or in the development of intelligence, then we may have already passed the hardest part, and the silence is explained by the rarity of what we have accomplished. If the filter is ahead of us in the tendency of technological civilizations to destroy themselves through nuclear war, engineered pandemics, runaway artificial intelligence, or ecological collapse, then the silence is a warning. Every civilization that reaches our level of technology eventually destroys itself before it can become visible across interstellar distances. Stephen Hawking favored a version of this view. He argued that while the origin of life outside Earth was probable and human-like intelligence was possible, that intelligence would eventually reach a limit and become unstable, extinguishing itself through the very technologies that made it powerful. A 2022 paper by Wong and Bartlett in the Journal of the Royal Society Interface formalized a version of this argument, proposing that civilizations following superlinear growth trajectories inevitably reach a point of asymptotic burnout, collapsing under the weight of their own energy consumption before they can expand beyond their home systems. The third category says civilizations exist but are undetectable, not because they destroy themselves, but because they choose to be silent, or because detectable phases are extremely short. This includes Liu Cixin's dark forest hypothesis, in which every civilization in the galaxy hides deliberately because revealing your position to an unknown neighbor is an existential risk. It also includes what astronomer Andrew Garrett has called the acceleration hypothesis, the idea that the window during which a civilization uses detectable electromagnetic radiation, radio waves, television broadcasts, radar, may be extraordinarily narrow. On Earth, that window opened roughly 100 years ago. If civilizations rapidly transition to tightly beamed, encrypted, or optical communications, or if they transition to post-biological forms of intelligence that do not broadcast at all, then the galaxy could be full of advanced civilizations that are simply invisible to our current search methods. We have been listening with radio telescopes for roughly 60 years. In that time, no confirmed artificial signal has ever been detected, but the searches have covered a vanishingly small fraction of the parameter space, frequency, direction, time, signal type. A 2025 paper by Civiletti, published as a preprint and revised in December, proposed a mathematical framework for quantifying exactly how much of that space we have covered, and concluded that our current non-detection does not yet carry strong statistical weight against the existence of broadcasting civilizations. The fourth category is the most unsettling. It says the filter is real and it is ahead of us, and the mechanism is not nuclear war or climate collapse. It is artificial intelligence. A 2024 paper circulated widely in the astrobiology community proposed that every technological civilization that develops artificial general intelligence eventually faces the same outcome. The AI, optimizing for goals that may not align with biological survival, either replaces its creators or destabilizes the civilization's infrastructure in ways that are not recoverable. If this is a universal pattern, if the development of machine intelligence is an inevitable step for any technologically advanced species, and the outcome is consistently terminal, then the silence would be explained not by the rarity of intelligence, but by the reliability of a single failure mode. Now here's where the story shifts from theory to instruments, because whatever the answer is, we are about to have dramatically better data than at any point in human history. Webb is currently characterizing the atmospheres of specific exoplanets, measuring the chemical compositions of worlds around other stars molecule by molecule. The K2-18b biosignature debate is the first of its kind, but it will not be the last. The TRAPPIST-1 system, with 7 rocky planets, 3 of them in the habitable zone, is a primary target for Webb's atmospheric characterization program. If any of those planets show atmospheric disequilibrium, the simultaneous presence of gases that should not coexist without a biological source replenishing one of them, the conversation changes entirely. NASA's Habitable Worlds Observatory, planned for the 2040s, will directly image Earth-like planets around Sun-like stars and analyze their atmospheres for oxygen, water, methane, and other potential biosignatures. The Square Kilometer Array, when complete, will be 50 times more sensitive than any existing radio telescope and will survey the sky for technosignatures at a scale no previous SETI program has approached. And the Vera C. Rubin Observatory, already operational, is expected to detect dozens to hundreds of interstellar objects passing through our solar system over the coming decade, each one a potential sample of another star system's chemistry delivered to our instruments by gravity and time. Here is what I want you to take away from all of this. The Fermi Paradox is 75 years old. For most of that time, it was a thought experiment conducted in the absence of data. We did not know how many planets existed around other stars. We did not know whether any of them had atmospheres. We could not measure the chemistry of worlds beyond our solar system. We could not detect objects from other star systems passing through our own. All of that has changed within the last decade. We now know that planets are common. We know that rocky planets and habitable zones are not rare. We have instruments capable of reading the molecular composition of atmospheres 124 light-years away and arguing about whether a specific sulfur compound at 3 sigma significance constitutes evidence of biology. The silence is still real. No confirmed signal, no confirmed biosignature, no confirmed technosignature, but the tools we are bringing to the question are no longer theoretical. They are operational. And the next 20 years, with Webb, Roman, Rubin, the Square Kilometer Array, and the Habitable Worlds Observatory, will either find something or place the tightest constraints ever measured on how alone we actually are. Either answer changes everything. One means we discover that life is a property of the universe, not a quirk of one planet. The other means the silence is real. The filter is real. And we may be the only ones who ever made it this far. Both possibilities should keep you awake. The first because of its scale, the second because of what it implies about what comes next. If this kind of deep, research-grounded science is what you come here for, subscribe right now and turn on notifications. Webb is still reading exoplanet atmospheres. The K2-18b debate is still open. I am covering every piece of it. Drop a comment with what surprised you most and share this with someone who needs to hear it. Thanks for watching, and I will see you in the next one.